When you look up at the sky, it just looks like a whole lot of empty space. But if you're a pilot, you know it is anything but empty. The air itself, this invisible ocean that we all live at the bottom of, is this incredibly dynamic, powerful force that completely changes how an airplane is able to fly. So let's dive into this invisible ocean and really get a handle on the challenges it holds.
Well, the answer is the very air the plane is flying through. It's a pilot's constant partner, but it's also a constant challenge. And a pilot who doesn't respect it and understand it is, well, they're flying blind, no matter how clear the sky looks. Because on any given day, the air itself can turn on you.
And this is what's really at stake. Thin air, as we're going to see, directly attacks the three things that keep a plane in the sky. It cuts down on engine power because there are just fewer oxygen molecules for the engine to breathe and burn. It reduces thrust because the propeller or the jet has less stuff to grab onto and push against. And, crucially, it reduces lift because the wings have less air mass flowing over them to generate that force that keeps you airborne. This isn't some minor tweak, it's a fundamental hit to the aircraft's ability to perform. Okay, so to really get this, we have to stop thinking of air as nothing. We need to start thinking of it as a physical substance, a fluid with properties that we can actually measure. And that right there is the key thing to wrap your head around. The air all around us isn't a vacuum. It is a fluid. It has mass, it has weight, just like water. It pushes, it flows, it has substance, and a pilot has to deal with all of it. So what is this stuff actually made of? Well, it's mostly nitrogen. But you see that 21% oxygen? That's the magic ingredient for most aircraft engines. It is literally the fuel for the fire. So when we talk about air getting thinner, what we really mean is there's less of everything in a given chunk of sky, including less of that absolutely critical oxygen. And all that air, it has weight. A lot of it. Just imagine a giant column of air stretching from the top of your head all the way to the edge of space. The weight of that entire column pressing down on you, that's atmospheric pressure. So it makes sense that the higher you go, the shorter that column of air is above you and the lower the pressure gets. Now, because pressure and temperature are changing all the time, all over the world, engineers needed a fixed yardstick, a baseline to measure aircraft performance against. And this is it, the standard atmosphere. It's this universally agreed upon model where at sea level, the temperature is a perfect 15 degrees Celsius and the pressure is exactly 29.92 inches of mercury. Every single performance chart, every flight manual, it's all based on this. It's the perfect day against which all the real, messy days are measured. Of course, the real world is almost never standard. Pilots are constantly dealing with conditions that are way hotter, colder, or have totally different pressure. So how on earth do you create a reliable baseline for your flight when the atmosphere itself is constantly changing the rules? Well, the first step is to isolate the effect of pressure. What a pilot does is set their altimeter to that standard, 29.92. The altitude then shows is called pressure altitude. It's basically answering the question, okay, let's just forget about temperature for a second. Based only on the pressure right now, what altitude does the standard model say we're at? It's the first major correction for reality. But pressure? That's only half the story. The real secret sauce, the number that truly tells a pilot how their aircraft is going to perform, is the one that combines pressure with that other huge variable, temperature. This is what we call the feels-like altitude. Let's make this totally real for a second. Imagine we're sitting in a plane and our pressure altitude is reading 5,000 feet. So the air pressure is what you'd expect at 5,000 feet on a standard day. But what if it's not a standard day? What if it's a really hot day? Here is exactly what's happening on a molecular level. On a standard day, the air molecules are all packed together pretty nicely. The air is dense. But when you heat that air up, say it's 20 degrees Celsius hotter than standard, those molecules get a jolt of energy. They start zipping around like crazy and spreading way, way out. The air expands and becomes much less dense, much thinner. And that brings us to the big one, the whole point of this explainer, density altitude. It's simply the pressure altitude corrected for that non-standard temperature. It's not a physical height you can see or measure with a ruler. It's a performance altitude. It is the altitude the airplane's engine, its propeller, and its wings actually feel like they're flying at. So let's go back to our plane at a pressure altitude of 5,000 feet. On that hot day, the density altitude is not 5,000 feet. Nope,
It's over 7,000 feet. The aircraft is physically at 5,000 feet, but it's going to perform like it's struggling through the thin, unforgiving air you'd find way up at 7,000 feet. This shows you exactly how much heat robs an aircraft of its performance.
And this isn't just some academic number. It has serious life or death consequences. On that standard day, this plane needs 790 feet of runway to take off. But on the hot day, with that density altitude of over 7,000 feet, it needs almost 1,000 feet of runway. That extra 200 plus feet could easily be the difference between a safe takeoff and running out of pavement. But wait, there's more. Pressure and temperature are the big two, for sure. But there's another, often overlooked factor that can take a bad situation and make it even worse. And that's humidity. So here's a little pop quiz for you. If you take a box and you fill it with moist, humid air, and then you take an identical box and fill it with nice, dry air, which one weighs less? The answer is completely backwards from what you'd think. The moist air is actually lighter. Why? Because a molecule of water vapor, H2O, has less mass than the nitrogen and oxygen molecules that it pushes out of the way. So as you add humidity to the air, you are literally making it less dense. You're increasing the density altitude and stealing even more performance from the aircraft. Okay, let's tie this all together. Why do pilots obsess over these calculations before every single flight? Well, it really just comes down to two things: performance and safety. So the takeaway here is knowing the recipe for danger. High-density altitude, that thin, poor-performing air, is created by some combination of these four things: high elevations, hot temperatures, and high humidity. That's the trifecta for terrible performance. A pilot sees those conditions lining up and knows they need to be extra careful. At the end of the day, density altitude isn't just a number in a textbook. For a pilot, it's a crystal ball. It tells them how much runway they're going to eat up on takeoff, how well they'll be able to climb, and if they can actually clear those trees at the end of the runway. It is the difference between having a solid plan and just having a prayer. Which kind of leaves us with one last thought. We think of a pilot as being in total control of their aircraft. But are they? Or is every single flight really just a careful, high-stakes negotiation with an invisible, powerful, and constantly changing force, the atmosphere itself?